Hi, welcome to Futureproof Your Planet. I'm Esther, I'm a second year physics student at the university and I'll be your host. This is going to be a webinar series going over how different subjects can help us future-proof our planet. Today's episode is for electrical engineering and I'm joined by Dr. Robin.
Hello.
You're going to be watching a video of his going over how we can power up the grid and use robots to help become more sustainable. And afterwards we'll have a Q&A section where you guys can ask questions to him.
Hi, I'm Dr. Robin Preece from the University of Manchester, and I'm here to talk to you about how we can future-proof your planet by getting our power systems to net zero. So we're here in the Net Zero Lab at the University of Manchester, and this is one of the teaching labs that we use on our electrical and electronic engineering courses to teach about how we can transition to net zero. So net zero is all about the balance of how much carbon we produce and how much carbon we take out of the atmosphere. And we want to get that to zero, and the UK's pledged to do that by 2050. Now, a big part of that is all about electrifying and decarbonising energy and our energy consumption. And the current government has actually pledged to try and get to green energy by 2030. Now, that means all the fossil fuels that we currently use, we need to stop using them and we need to replace them with more and more renewable energies or with things like nuclear, which are much, much lower from a carbon perspective. Now, doing that is a real challenge. So a big part of decarbonising our energy is all about decarbonising and electrifying our big sectors like heating and transportation. So at the moment, most cars actually consume fossil fuels, consume petrol, and we're going to shift that over and use electric vehicles instead. But doing that is not very simple for the electricity grid because every vehicle is essentially the same as connecting another house. The amount of energy an electric vehicle uses is about the same as a house. So the grid isn't really set up for that and can't cope with all that electricity. At the moment, only about 1 in 30 cars are actually electric vehicles. So that's a lot more electricity that's going to need to be used. It's basically like doubling the grid, doubling the amount of electricity that we need to get through our power system. And that's a real challenge. And that's just vehicles. If we do heating as well, if we move from using gas boilers to instead using things like heat pumps, that's going to be another doubling of the grid as well. Obviously, we can't build all of that infrastructure at one time, so we have to be cleverer about how we use the electricity we have, how we get that through the networks, and how we get that through to consumers at the end of the day. Now, doing that is a challenge, requires things like smart controls, new types of materials, new ways of controlling things, lots of coordination across lots of different electric vehicles all across the country. And that's the kind of challenge that electrical engineers are solving. It takes things like communications, control, design, sensing, new materials. All of that stuff is stuff that we do. And we've got to do that as well in a way that is safe, secure, green, reliable. So this balance of affordable, sustainable energy is one of the biggest challenges facing actually the whole planet right now. It's not just the UK that's trying to do this, and that's also one of the challenges. The fact that every single country in the world is pretty much trying to address these problems at the same time. That means that there's also struggles with getting like global supply chains in place in order to be able to get the equipment you need, even the skilled workforce. There's just not enough engineers. And so we want you to come to Manchester, train to be an engineer, an electrical engineer in order to solve these problems. But it also means that if you do that, you'll have the skills that will be able to take you pretty much anywhere in the world as well. The good thing is that electricity works the same wherever you are in the world. So here at Manchester, we are solving these kinds of problems. We're working on this. We're doing research here to try and tackle these things. We use our high voltage lab, which is the biggest high voltage lab of any university in the UK. We use that lab to test new materials, to test new products, zap them with 1,000,000 volts and see if they're able to survive out in the real grid. We're using that. We're also using spaces like this to develop new types of control, to see how to control things like solar panels and electric vehicles and to coordinate them all so that they're working together so that we can get the most out of the electricity grid that we've got right now, because it's going to be a challenge to build another 2 or 3 grids in the next decades. And we're working with big companies in the area as well. We work with National Grid a lot, and we work with them to develop more resilient power systems. So systems that are able to survive the kind of climate challenges that we're going to have, more lightning, more storms, extreme wind, flooding, extreme heat, all of those kinds of challenges. We need a network that's able to survive those and keep operating, particularly if we're more reliant on our electricity in the future. So we need engineers to come and future-proof the grid itself. So obviously there's a lot of challenges left to solve with the electricity grid, but that's just one part of electrical and electronic engineering. And if you come to Manchester, there's lots of different ways that you'll be able to help contribute to future-proofing your planet.
We're here in one of the robotics research labs in the Department of Electrical and Electronic Engineering. And you might be wondering how robots can help future-proof your planet and help with the big challenges of net zero. Well, consider the scenario that by 2050, we need 80,000 more wind turbines. That's 250,000 wind turbine blades that need inspecting, 10 million bolts that need maintenance and tightening. To be able to do that with current technologies, we would need a new workforce of 400,000 operators and technicians. And that's just in the UK alone. Globally, we're going to need nearly 200,000 new wind turbines. So if we can't do it with people, what can we do it with? Well, robots are one of the solutions that we're exploring. So these environments that we need to maintain are often in really remote locations, and they're often difficult to access, or the ways to access them are really carbon intensive. If your wind turbines are in the middle of the North Sea, you need to send a big ship, a helicopter. There is a huge carbon footprint associated with that. Imagine a world where robots lived on the wind turbines, that they lived in the nuclear facilities or on the solar farms, that were doing the maintenance and operations with human oversight to make sure that they're doing the correct activities. But that cuts down the carbon emissions, and that keeps the fleet of energy generation assets going. It keeps our lights on. Our world runs on electricity. Our world runs on technology. To secure that future and make sure that it's sustainable for not just your generation, but the next generation, we need to invest in the people, in the skilled engineers. And that's what we do here at the University of Manchester in the Department of Electrical and Electronic Engineering. To build a robot, which is a highly complex system, you need all sorts of technologies. You need motors, you need sensors, you need the software that underpins it all. Now, all of those technologies are used in our everyday lives, from your washing machines to your computers, your phones, your cars. So developing that technology is not just beneficial to robotics, but it's also beneficial to the wider world. And when we developed these robots that are going to help the net zero assets and help maintain them and run them, we can also use them in other areas as well. The UK was a pioneer in the Victorian era of building urban infrastructure. Our road network, our rail network, the sewage system, the utilities, they were all developed as world-leading areas. But now they're aging assets, and they need a significant amount of investment to maintain and to upgrade them. And to do that efficiently, the use of robotics is going to be critical. They can access areas that humans can't. They can monitor things safely, taking people out of harm's way. But they're never going to be fully autonomous. We are always going to have people there behind the robots, building them, designing them, maintaining them, and operating them. And once we've got them in those challenging environments, we can also have wider societal benefits. We can start using those robots in our day-to-day lives, helping us with social care, social assistive robotics, helping us with surgical robotics and healthcare robotics as well. So how robots can help future-proof your planet? Robots in the future will be in every single aspect of your life. But even if you're not interested in robots, the technology that goes into them is critical to keeping our world running. Our world runs on electricity. Our world runs on technology. Engineering is fundamental to this. Be it from the power grids, the networks, the energy generation, through to our phones, electrical appliances, to the robots that are going to help sustain our future. We need engineers to help develop that next generation of technology. That's what we'll train you in. We'll train you in those core technologies that is going to help future-proof your planet and lead to a sustainable future.
Welcome back. We're going to start the Q&A section. So the first question is, how is nuclear energy better than thermal power?
Okay, so nuclear energy basically works by using radioactive material to heat up water to make steam to push turbines around, and then we get the electricity from that. The rest of our thermal energy usually comes from kind of burning fossil fuels. So we burn coal or we burn gas, and again, with coal we use that to heat water, make steam. With gas, we just burn the gas and use that to drive turbines. So they kind of have the same fundamental kind of mechanism. They usually are kind of similar in terms of their kind of scale, so we tend to build them at similar kind of sizes. The thing with nuclear is it's very, very low carbon. So there's very little carbon cost associated with it. Some associated with building the actual plant because it's a lot of concrete involved. But in terms of running cost, not very much at all. Obviously, with burning coal or gas, there's a lot of carbon released into the atmosphere, and so then that can have a big impact on the environment and on kind of global warming and things like that. The challenge with nuclear is obviously nuclear waste and then nuclear waste storage. But I guess my position on that is a little bit like that is definitely a problem and is definitely an issue that needs to be considered, but it's over a much longer time frame. It's a little bit like if your house has like subsidence and is sinking, but it's also on fire, and so you deal with the fire first. So I think that's probably why we've transition away from things like coal and gas as quickly as possible. In the UK, we've already stopped coal. Gas will hopefully end in the kind of 30s. That's at least the plan that the government has.
Yeah, perfect. So our next question is, how realistic is a full shift from fossil fuels by 2030 or 2050? And what roles might transitional technologies like carbon capture or nuclear play into that process?
Yeah, so in the UK, we have something called Clean Power 2030, which is the target that's been set by the government and by something called NESO, the National Energy System Operator. The plan there is to be able to run the system with like zero carbon sources 95% of the time by 2030. That is ambitious, I would say. It is on the edge of plausible. Like it is possible to achieve, but it will be a real challenge, and we have to absolutely run at it immediately if we're going to make it there. By 2050, yeah, we could definitely be operating at that levels. That's not so much out there in the realms of possibility. In terms of how we do that, the real challenge, the reason that it's set up as a 95% of the time target is because there will be times when we just won't have wind. We won't have solar power available. We might have an outage on a big nuclear plant or something like that. And so we need to have something as a backup. And at the moment, our backup is gas. In the future, that backup might be other things. It might be things like hydrogen. It might be things like large amounts of batteries and stuff. But typically, batteries only store enough energy for 1 or 2 hours. And obviously, if this period of low wind, no solar lasts multiple days, you need something that can get you through that period. Carbon capture storage is an interesting one. So the idea there is you could still burn gas, but instead of releasing it into the atmosphere, you capture it and then you store it and you lock it away somewhere. The challenge with most of the CCS kind of at scale is that they've really, really struggled to scale up. So they quite often work for small areas, and they might be a really good solution for, say, like very hard to decarbonize industrial plants, things like steel manufacturing, stuff like that. But it might be a real challenge to scale that up to kind of like a national level and still burn gas in terms of like a gas power plant. So I'd be a little bit cautious about expecting carbon capture storage to be the solution.
Yeah, you mentioned earlier a bit about hydrogen, and I want to ask, do you think hydrogen vehicles are more sustainable than electric vehicles?
So I don't know the full kind of life cycle carbon assessment. Typically, the issue with hydrogen in terms of is more a usability one as well. So I think if you ran all the numbers, they might come out as more sustainable. But the challenge is just access to hydrogen. So the benefit electric vehicles have is there is an electricity network all across the country already, Most people already have access to that. They may not have a fast charger or a driveway, and there are certainly issues with how they access that, but the accessibility of electricity is so much higher than hydrogen. We will never build large-scale hydrogen distribution networks. So I think hydrogen for vehicles is more likely to make sense maybe in very specific regions where they have hydrogen production locally. So you can imagine situations where you might have an electrolysis plant at a port, and all the vehicles around that port are all able to use it. Maybe the local town can have a fleet of hydrogen buses, because you don't have that complexity of how do you get to the hydrogen. But at a national scale, I think, yeah, you're unlikely to see hydrogen distribution work, like so that you or I could go and fill up our hydrogen vehicle very easily.
Yeah, perfect. And what do you think is the major stopping block in transitioning from clean energy in the UK?
The major challenge. So there's issues related to just getting enough electrical infrastructure built quickly enough. So the numbers are pretty staggering. So if we wanted to put all of heating onto the electrical network, that basically requires us to build another electrical network, kind of similar in size to the one we've already got. If you wanted to put all of transport onto the network, that's another electrical network as well. Like the average electric vehicle uses as much energy as a house. And so some houses have 2 of those, so that's a lot of energy. Yeah. And the infrastructure that we have isn't geared up for that. And so we either have to do a lot more local generation. So if you generate your electricity on your house with solar and then immediately charge your vehicle, you don't have to put that energy through the grid. And so that's a much more efficient way of doing it if you can directly generate at the source where it's being used. But then that requires everyone to have solar. Not everybody's in a position where they can do that. You obviously don't always have enough solar energy to meet all your demands. And so you end up in this situation where you still need a large amount of grid infrastructure upgrade. You also need large amounts of distributed generation. Maybe you need batteries in people's houses as well to help kind of buffer when they need to use the energy and when it's available to be created. And just that huge amount of kind of infrastructure build is probably the biggest challenge. We essentially have spent the last kind of like 20 years maintaining our network at pretty much the same level. And actually electrical demand has decreased because energy efficiency has improved. And so we've actually been using less and less energy. Now that's starting to ramp up so fast. We need people, so we need lots more people trained as electrical engineers, and we also just need access to all the kind of infrastructure and supply chains. Everyone's trying to buy this. There isn't enough copper. You need to be able to mine the copper, and also every single country in the world is pretty much doing this at the same time. So it's not just our challenge to decarbonize and electrify, it's like a global challenge. And so that's nice from the perspective that any skills you develop in this area will mean that you can travel globally and basically find a job anywhere. That's the nice thing about electrical networks. The electricity works the same everywhere. And so you can be an electrical engineer anywhere. But it makes it a challenge in terms of how society kind of makes that transition.
Yeah. When do you think net zero will be achieved in the automotive industry as a whole, considering combustion engines are still prominent today?
Yeah, I'm not too sure what the kind of targets are. I remember there being a target at some point. I remember seeing it on the news. It was kind of like 2030 or 2035 we'll only be selling electric vehicles, and maybe that's still the case, or maybe that disappeared. I definitely noticed that pretty much every car advert you see these days is always for an electric vehicle. You almost never see an advert for kind of a combustion engine vehicle anymore. So I know that there's a massive growth in the number of electric vehicles being sold, but I think at the moment it still only represents something like 2% of vehicles in the UK are EVs. So there's obviously just like a huge gap. And yeah, you're looking at lifetimes of existing vehicles of maybe 10 to 15 years or something before that vehicle drops off from the kind of fleet. So let's say maybe 2050 is realistic. Yeah. Maybe if we stop selling combustion engine vehicles in 2035 and then another 15 years for all the existing ones to kind of disappear, yeah, you're probably looking at that kind of time period, which is also probably the kind of time period you need to be able to get enough charging infrastructure installed to make that a possibility, to make that workable.
Yeah, so I feel like 2050 is the big year for everything coming in.
Everything happens in 2050.
The world's solved at 2050.
Exactly.
Is tidal energy a viable untapped resource for the UK's long-term energy mix?
Yeah, tidal energy is an interesting one. So the way tidal energy typically works is you'd find an area and you'd build essentially a kind of a dam. So, and then you let the tide bring the water in, you dam it, you store the water, and then until the tide goes out, you then have like a height difference in water. You then open up the gates, let the water run out, and as it goes out, it flows past turbines and generates energy that way. The biggest concerns usually with tidal energy are environmental ones, because you are by definition kind of flooding and repeatedly flooding an area. And so it can have quite a large kind of environmental impact. Obviously the UK is in quite an interesting position because it's an island, it has huge amounts of coastline. But I think up to now, we've not really done very much with tidal energy. The other option, which is kind of similar, is like wave energy. Mm-hmm. So that would be more you put devices onto the sea surface and they respond to the energy of the waves. But those can be, again, they can be quite challenging. In terms of how they build. They have to be able to deal with typically very, very high peak amounts of energy. So that the max energy they produce is really high, but the average energy is really low. And so it's very hard to build an efficient energy capturing device for that. So instead, the primary ones are still kind of offshore wind, onshore wind and solar. Yeah. And I'd probably be surprised to see those lose their dominance in terms of their position in the market, because they're already essentially the cheapest forms of energy we have. Yeah. So even without kind of subsidy. So yeah, I'd be a little bit surprised. Maybe tidal gives you a bit more kind of control. Maybe there's some element of a kind of inbuilt storage there, which is beneficial. But in general, I'm not sure if that outweighs the kind of environmental concerns associated with it.
Yeah, and we'll do our last question now. Would mining copper involved in production be considered unsustainable due to the resource depletion and energy-intensive process of mining?
So it's definitely energy intensive. It's definitely got a carbon cost. It's definitely not in any way 100% sustainable at all. But essentially, the major metals used in electricity distribution are either copper or aluminium. And both of those, aluminium as well, has high energy costs associated with like smelting in order to extract the aluminium. So yeah, so there's definitely a concern there, which is the kind of life cycle carbon assessment. But one of the benefits of them is essentially once you have gone through that process, these assets have an incredibly long lifetime. So there are transformers on the electrical network which are over 100 years old. They were built 100 years ago. They're still there. They're still working. So it's and if we were to retire that piece of equipment, we could then very easily extract that material and use it again. So even though there is certainly a cost associated with creating it over the kind of 100 or so year lifetime of the asset, it's probably justified, I think, and also in terms of the way that then enables you to utilize green sources of energy, renewables and things like that, and get your energy from much lower carbon intensive sources. So yeah, so kind of in the long term, it's important, I think, to look at the kind of the whole life cycle.
Thank you for answering all the questions and for the video today. So that's it for today's session. If you join us later next week, we'll go over other subjects and how you can future-proof your planet. If any of the questions are left unanswered, people will come to the YouTube comment section and answer them for you.